Hey everybody, welcome back. This is part 3 of my association series in statistics. I have an intro, very brief, go and watch that first. Part 2 is how categorical variables associate to each other, and this video is how quantitative variables are associated. We also call that correlation if it's a linear association. All this terminology, words matter, right? Alright, let's have some fun. Here's part 3. To assess association between quantitative variables, we create a scatter plot with the independent variable, also known as explanatory, on the x-axis, the dependent variable on the y-axis, also known as response variable. Then we calculate a correlation coefficient, R, a pirate's favorite variable, and we create a linear equation that best fits the data. This is easily done with technology. Again, we're going to use Staplin. The correlation coefficient, denoted by the letter R, is a measure of strength and direction of a linear association. The value of R ranges from -1 to 1, with values closer to 0 being weaker, and values closer to the extremes, -1 and 1, being stronger. A positive relationship means that as x increases, y increases as well. A negative relationship means that as x increases, y decreases. Here's some examples of scatter plots and their R values. A, R equals 0.5. This is a moderate positive relationship. B, R equals 0.90. This is a positive, strong positive relationship. C, R equals 1.0, positive 1. This is a perfect positive relationship. See how they line up perfectly? D, R equals -0.50, so this is a moderate negative relationship. E, R equals -0.90, this is a strong negative relationship. And F, R equals -1.0, this is a perfect negative relationship. Here's our example. To the right is some quantitative data. So we've got ice cream sales versus temperature. Temperature is going to be our X variable, the explanatory, and ice cream sales is going to be the response, or Y variable. Enter the data, being careful not to change the order. So when you go to Staplin.com and you click on linear regression, make sure that when you enter each column, column 1 and column 2, the two lists, you don't rearrange the order of any value, because these are actually paired pieces of data. So the temperature goes with the ice cream sales. They correspond to each other. And here's the scatter plot that we see. It looks linear and positive and fairly strong, but let's get some numbers to back that up. Click on Calculate Correlation and calculate least squares regression line, and we get R equals 0.958. That is strong. And here's our equation. Y equals -159.4742 plus 30.0879 times x. The equation here is in the form y equals a plus bx, where the intercept is a and the slope is b. Recall from algebra that the intercept is the y value when x equals 0. So when the temperature is 0 degrees Celsius, the predicted ice cream sales are -159.474. This is of course impossible, and it demonstrates why extrapolation is an unreliable practice. Extrapolation is making predictions far outside the range of the observations. So sometimes when you make a prediction, it's practically impossible. It doesn't make any sense to have a negative cost of ice cream or ice cream sales. Unless maybe you go into debt. Maybe that is practical. The slope is a little more telling. It tells us the change in y over the change in x. So for every 1 degree rise in temperature, we predict an increase of about $30 in ice cream sales. And that's a meaningful thing to know. Finally, click on Perform Inference to get your p-value. Now, the alternative hypothesis, you have a little drop-down menu. I chose beta greater than 0 because we had a positive slope here. If you suspect a negative relationship, you would choose beta less than 0. And if you didn't know what relationship you were going to get, you would choose beta does not equal to 0. And here our p-value is significant, 0.001. So this association is in fact significant. But again, we cannot conclude causation simply based on this observational study. We need to do an experiment. I'd gladly volunteer for an ice cream experiment, by the way. Now here's some practice. Here's data from 7 students. The question is there an association between SAT score and GPA? Let's find out. Here we are back at Staplet.com. So I want to click on Linear Regression T-Test. And again, it asks for the 2 variables, explanatory and response. So I'm going to enter those names. We're seeing if SAT is influencing or explaining an increase or decrease in GPA. And I'm going to enter the data basically as it is right here. Oh, really, really important. Don't mess around with the order. Don't try to sort them least to greatest or something like that. These are paired pieces of information. So the same student that got a 595 on the SAT got a 3.4 GPA. So we have to keep them in the same order. Otherwise, we're not performing the analysis properly. And I'm just going to put commas in between each of them. All right, the hard part is over, folks. Click on Begin Analysis. And here it is. This is our scatter plot. Looks like there's a positive upward trend. Now, this is a small sample size, so it's hard to really know for sure, but I see a positive upward linear trend. Click on Calculate Correlation. And this R value, remember, the closer to +1 or -1, the stronger. This is a strong, very strong model, 0.947, and it's positive. Now click on Calculate Least Squares Regression Line. We get a lot of output here. First of all, they add a line to our graph that best fits the data. It minimizes the distances between observation and prediction, also known as residuals. This is called a residual plot, and what you want to see here is random scatter. If you see a pattern, if you see too clear of a pattern in the residual plot, it means that a line is not the best model. You may want to explore curved options like exponential, parabolic, hyperbolic, logarithmic, and so on. Okay, so if I keep scrolling down, here's my equation. The y-intercept is 0.0974. That's what we would expect your GPA to be if you got a 0 on the SAT, right? And again, sometimes that's not a practically useful number. But this slope is 0.0055. So for every additional SAT point, 1 point, in SAT, we expect the GPA to go up by about 0.0055. That's how you interpret that. Is for every unit increase in the X variable, you expect a increase in the Y variable of whatever the slope is, 0.0055. N is the sample size. S is the standard deviation of the residuals. So that's a measure of how spread out the difference between observation and expectation is. So the smaller that number is, the closer the points will clump around each other. And the R squared is the percent of, it's called the coefficient of determination. It's the percent or proportion of variation in the Y variable that's accounted for by the linear model, which is the relationship between X and Y. Don't worry too much about that. We worry more about R, which tells us the strength and direction. And Staplet is great. We can calculate other models like quadratic and exponential, very common ones, to get a different model and see if it's a better fit, okay? Now, even though this is strong, it may not be significant. So I do want to click on this last option here, perform inference, and we do get a p-value that's significant. It's below 0.05 and even lower than 0.001. So this is a highly significant and very strong positive linear association. Okay, everyone, thanks for watching. I hope you had a great time doing math with me. Don't forget to subscribe to my videos on YouTube. Click the bell for the notifications so that you can get every video as it's released and continue your journey, your exploration through the world of mathematics. What an exciting time it is to be a student. I'll see you next time. May the math be with you.